In this video, we're going to introduce a graphical perspective on differential equations. We're going to start off with a simple example and then gradually add in some complexity. The simple example we'll begin with is dy dx equals cos of x. We've seen this before in the sense that we could say y prime equals cos of x, or y equals the integral of cos of x dx. We know how to solve that and evaluate that. We'll do that in a moment. But what we'd like to remind ourselves of first is that the dy dx term, what that means, is literally the slope of the graph of y. If we don't know what y looks like, we at least have information about its slopes at any point here, x. And here it is written out in a sentence form. We're looking for a function y. We're looking for y equals. But what we know about that function is that the slope at any point is defined by cos of x. Well, let's start off with returning to what we know, which is if the derivative of y with respect to x is cos, then the y is the antiderivative of that, or the integral of cos, and we know that that's sine of x plus c. In this case here, notice plus c because we are just integrating the cosine function, and we can check that by taking the derivative. The derivative of sine of x plus c is just cos of x. Check. So we have a general solution in the sense that we can scale this up and down by a vertical shift c. Now, let's take a look at the graphical perspective on this on the next page. In the graph below, you see what's called a slope field for this formulation. We're going to pretend we don't know what the answer is, we don't know what y equals, and just work with this. First question is, how was this picture generated? Well, if we take a look at any point, like let's say 0, 0, you see there's a line there, and it looks like it has slope 1. Well, at x equals 0, cos of x is 1, but we are interpreting that now as dy dx, which is a slope value. So on this axis, we have literally y. On the axis this way, we have x. And what we do is we pick an x value, sub it into our formula, and it doesn't give us a point, it gives us a slope at a point. Notice all these other points with x equals 0, no matter what the y is, there's no y in this calculation, we get a value of 1, and we draw that as a slope of 145 degrees. If we scan across a bit further, let's go out to 3.14, or pi, as most people would call it. 1415, etc. When we evaluate the cosine there, cosine of negative pi is actually negative 1. Sorry, cosine of pi is negative 1. Well, that corresponds to a slope of negative 1 that we would draw at all those locations. And you can see as we pick different values, say pi over 2, cos of pi over 2 is 0, we draw that as a slope of 0, slope of 0. So this construction here just uses the formula we were given and treats different x values being subbed in to get response values, but the key thing is those values of cos here represent slopes on the graph we're trying to draw. Going back to what this means, we are trying to Going back to what this means for our solution, we want a function that always has this defining its slopes. So if I try to sketch this, I want to find or sketch a graph that looks like it's following these slope lines. And so pretty quickly we can get a graphical sketch of the curve, and lo and behold, this looks an awful lot like sine of x. Or if we start somewhere else, we get something that also follows the lines. And what I mean by follows the lines is if you end up touching one of these lines, you have to sketch your graph with the same slope. Why is that the rule? Because we're sketching y, and the slopes of y are defined by cos of x. That's how we drew those lines in the first place. And lo and behold, we get other solutions that look like, this like plus 1 and a bit, say 1.2. Oh wait, all of these are of the form y equals sine of x plus c. This graph can be vertically shifted up and down, and all of them are going to satisfy this pictorial or this graphical solution. So what are we doing? We're trying to be able to sketch a solution, maybe without a formula, basing it only on the information provided through a differential equation. The slope field only needs the derivative equals some formula for us to be able to work with it. So it's a very powerful new technique that doesn't involve actually integrating anything. And in mathematics, it's tremendously helpful to have alternative methods, some which will work in some scenarios when the other options available to us might not work. That particular example was fairly simple. What we're going to look at more generally is expressions where we have a slope, but we might have x's and y's in the right-hand side. For example, dy dx equals minus x over y, x times y, y minus x. And here's where the complication comes in. This is why we need slope fields sometimes. These forms cannot be directly integrated to find y of x. Remember the last example we had was dy dx equals cos of x. And so y was just the integral of cos of x dx. That's how we could invert the derivative. The integral is the antiderivative. However, here we would have 1/2 x minus y dx. Now we've covered this before, but let's reinforce it again. We cannot integrate this if we have a mix of x's and y's which are related and interrelated values with x. We have to stop at that point. There's nothing we can do with this integral the way it's written right now. So just don't is the answer for that. However, we still have a differential equation. Someone says that there's a function y that somehow its slopes are being defined by this formula. What else can we do? We can go to our slope fields and see if we can get a graphical perspective on this. So let's sketch that slope field for the scenario. Notice in this one, we actually have to include x and y. If someone tells us x and y, then we can find the slope. And so we build a little table. There's various ways to sketch this out, but usually we start around the origin and maybe we increase our x values first. So we have the origin and these 2 points here. Those are the locations. And then at those locations, we draw the slope that we compute. At 0, 0, we get a slope of 0. At 1, 0, that's 1 minus 0, that'll be 1/2. At 2 times 0, that's 2 minus 0, that's 2 times 1/2 is 1. So we draw those as slopes at the corresponding locations. Slope 0, slope 1/2, and slope 1 is 45 degrees on this even scaled axis. Then maybe we go up to 1 and do the same thing. 0, 1. 0 minus 1 is negative 1 times 1/2. That's negative 1/2. 1 and 1, that gives us 0. 2, 1, that's 2 minus 1 times 1/2. That'll be positive 1/2. These points all have y equals 1. All right, and then it was negative 1/2 slope, 0 slope, and then positive 1/2 slope. You can see that we're getting a sketch roughly of the shape here. Let's actually go back a couple more steps. Let's go to negative 1 and negative 2 for x. Negative 1 minus another one is minus 2. That's minus 1 slope. If we do that, we'll get minus 3/2 slope. So minus 1, 45, a little steeper than 45 here. And we can start to see a pattern. As we move left, the slopes become more negative or steeper negative. When we had, let's say 2, 2, we would get a 0 slope again, and then the negative slopes happening. So you can do more table values if you like, or look for patterns and just sub individual coordinates now that we have the habit. Same idea as we move right, the slopes get more and more positive. Upright, slope 1, slope 1.5, half slope, 1 slope, 3/2, and even steeper. And just by crossing our eyes a little bit and blurring the view, we can see what the solutions might look like, what graphs that follow these slope lines might look like. We can in fact even try to do that now. Pick a starting point, let's say here, and the graph might look something like this. It actually has to go a little, it has to match the slope of whatever lines we drew when we touch them, but we'd have some kind of shape like that. In this kind of scenario, oh, this is interesting. This one actually seems to lead us to a straight line solution. Some other ones might come up like this. And so we get y as a function of x solutions that actually have some interesting properties to them themselves. We don't know how to get the formula for this, but we can take a look at their graphical shape based on the slope field that we just constructed. So this technique allows us to use our idea that dy dx represents slopes to lead to at least graphical sketches of what the solutions might look like, even if we can't get to a formula.